All right, let's talk about radical expressions. You know, these things with the funny-looking square root symbols. They can look super intimidating, I get it, but I promise you, it's like they have a secret language, and today, we are going to learn how to speak it.
So take a look at this. The cube root of x times the fifth root of x. Right now, this probably looks like a total nightmare, a real head-scratcher. But hang in there, because by the end of this, you're going to have the key to unlock this whole thing, and you'll see the answer is actually pretty straightforward.
Okay, so let's just dive right in. To crack any code, you've got to start with the absolute basics. So what is this little checkmark symbol really asking us to do?
At its heart, this whole idea is really simple. The radical sign, it's basically an unsquaring machine. So if you pop a number like 16 in there, it asks one simple question. Hey, what number times itself gives me 16? And of course, we all know the answer is 4. It's just the exact opposite of saying 4 squared is 16.
Now, every language has its own vocabulary, right? So let's get these two words down. The number or the variable inside the symbol, that's called the radicand. And that tiny little number tucked away in the corner, that's the index. It tells you what kind of root you're looking for. A 3 means a cube root. And here's the important part. If you don't see an index at all, you just assume it's a 2, a plain old square root.
And this brings us to a huge rule you've just got to remember. When you have an even index, like a square root, you can't have a negative number inside as your radicand. I mean, think about it. No real number times itself is ever negative, right? But with an odd index, like a cube root, it's a totally different story. Negative numbers are perfectly fine, because, negative 5 times negative 5 times negative 5 is negative 125. That difference is absolutely crucial. All right, we've got the basic words down. Now let's talk about the grammar. These are the rules that are going to let us actually play with radical expressions, combine them, simplify them, and turn these messy-looking problems into nice, clean answers.
First up is the product rule, and this one is a super useful tool. It just says that if you're multiplying things inside a radical, you can split them up into their own separate radicals. This is amazing for simplifying. So take the square root of 12. 12 isn't a perfect square, but one of its factors is 4. So we can split it into the square root of 4 times the square root of 3. We know the square root of 4 is just 2, so the whole thing cleans up nicely to 2 times the square root of 3.
And you guessed it, the same exact logic works for division. We call this the quotients rule. The radical of a whole fraction can be split into a fraction with 2 radicals, one for the top, one for the bottom. Same principle, just applied to fractions, and it helps us simplify things a ton.
So what about adding and subtracting? Well, this is where it helps to think back to basic algebra. Remember, you can only combine like terms. 3x plus 2x is 5x. It is the exact same idea with radicals. If they have the same index and the same radicand, we call them like radicals, and you can combine them. So 3 times the square root of 2 plus 2 times the square root of 2 is just 5 times the square root of 2. Easy. You just add the numbers out front.
But what if, at first glance, they don't look alike? Take the square root of 12 minus the square root of 48. They don't look like radicals. But wait a minute. We can use that product rule we just learned to simplify both of them. The square root of 12 becomes 2 times the square root of 3, and the square root of 48 simplifies down to 4 times the square root of 3. And look at that. They were like radicals in disguise all along, and now we can subtract them no problem.
Okay, let's tackle what is, I think, for most people, the most confusing part of all this. What to do when you have a radical in the denominator of a fraction. It has this fancy name, rationalizing the denominator, but the idea itself is actually pretty simple.
So why do we even do this? Well, honestly, it's mostly about keeping things tidy and consistent. Think of it as a rule of mathematical etiquette. It's just considered bad form to leave a radical hanging out in the bottom of a fraction. So we have a way to clean it up.
For the simple cases, the fix is super easy. All you do is multiply the whole fraction by a clever version of the number 1. You just take the radical from the bottom and put it over itself. When you do that, notice the denominator becomes the square root of 2 times the square root of 2, which is just 2. Boom! The radical on the bottom is gone, and our fraction is in its proper, tidy form.
But what if the denominator is more complicated? Like, what if it's 2 terms, say the square root of 3 minus the square root of 2? For that, we need a secret weapon called a conjugate. A conjugate is just the same 2 terms, but you flip the sign in the middle. And here's where the magic happens. When you multiply an expression by its conjugate, the messy middle radical terms always cancel out. And here we can see it in action. You multiply the top and the bottom by the denominator's conjugate. Now just watch what happens on that bottom line. The middle terms, a positive square root of 6 and a negative square root of 6, they cancel each other out perfectly. You're just left with 3 minus 2, which is 1. And just like that, poof, no more radicals in the denominator. It's a pretty slick trick.
Okay, we have covered all the rules, the grammar, the etiquette. Now it is time for the big reveal. This is the one idea that connects all of this stuff to something you're probably way more comfortable with already: exponents. This right here is the Rosetta Stone. It translates the language of radicals into the language of exponents.
So let's start with something familiar, a rule you definitely know. When you multiply two things with the same base, what do you do with their exponents? You just add them up. So x to the m times x to the n is just x to the m plus n. Simple. We all know that.
So what happens if we get a little weird and apply that same rule, but using a fraction as an exponent? Let's just try it. What's 5 to the power of 1/2? Well, if we multiply it by itself, the rule says we add the exponents. So 1/2 plus 1/2 is just 1. The answer has to be 5 to the power of 1.
Now hold on, think about what that actually means. We just found a number that when you multiply it by itself gives you 5. By definition, what is that? That's the square root of 5. So 5 to the power of 1/2 is just another way of writing the square root of 5. This is it. This is the secret key. A radical is really just a fractional exponent in disguise.
And this brings us to the universal translator. For any fractional exponent, it's super simple. The denominator of the fraction is the index of the root, and the numerator is the power. That's it. So x to the power of 2 over 5 is just the fifth root of x squared. You can now flip back and forth between radicals and exponents whenever you want.
So now that we have this Rosetta Stone, this secret decoder ring, we can go back and solve problems that seemed totally impossible before. Let's put this all together and see the kind of power it gives us.
Remember this guy from the beginning, the cube root of x times the fifth root of x. Now, if you only use the rules for radicals, you're stuck. There's nowhere to go. But now we can just translate it into the language of exponents.
Okay, step 1. We translate it into exponents. That gives us x to the 1/3 times x to the 1/5. Step 2, we just use our old rules for fractions and find a common denominator, which is 15. Step 3, now that the bases are the same, we can just add those new exponents, which gives us x to the power of 8 over 15. And finally, step 4, we translate it back into radical form, the 15th root of x to the 8th power. And just like that, we solved it.
And really, that's the big takeaway here. Radicals aren't some weird, separate, scary branch of math. They're just exponents wearing a clever disguise. And once you see that connection, a whole bunch of problems that seemed impossible suddenly become simple. Which kind of makes you wonder, right? What other impossible math problems are out there, just waiting for us to find the right secret key to unlock them?